Muted myself.
Please, Mike.
Okay, hey. Hi all. I am Jagor, coming now from Rimac Technology. I've been, most of you know me. I'm in this community now for 15 years or something. I did a lot of things, R&D, incident response, back in the day with Carnet colleagues, and latest, before my automotive life in Infigo, pen testing, mostly pen testing. And now for the last 3 years, I am doing automotive security. For me, car is a thing that goes from point A to B and nothing else. But I like technology. So why do we do this in automotive? Well, actually, United Nations discovered that cars are big computers on wheels, and they can crash into things when get hacked. So there you have this document, United Nations regulation number 10555. Sorry, with big United Nations stamp. That says that you have to take care of the cybersecurity while developing vehicle. 2.5 years ago, I talked in besides Varaždin about the cybersecurity of connected cars and ecosystems. Today we'll go a bit deeper into development itself. But bottom line, for those who don't know, nowadays you submit your crash test report that car won't crash you, and then you also submit your pen test report to the homologation body, and you cannot put a vehicle on the road without that. We do technology. We, in Rimac Technology, don't do the whole vehicle. We do parts. We do batteries, inverters, powertrains, battery management systems, a lot of different things. And we have to adhere to those boring standard of ISO 21434, which ensures that we took cybersecurity in mind when developing our products, which then go in the vehicle, because any vehicle, my most cheap Volkswagen outside, has a lot of different computers inside that need to communicate each other. And in case also of my cheapest Volkswagen now, it's connected to the internet. I have an app, I can connect to it. That means that, well, basically can get hacked. A lot of things got hacked. And now cybersecurity is a really big topic in automotive. But automotive does not know how to develop things fast. And automotive has a really different perception of software development than the rest of the world because of two constraints. One major one, well, the vehicle can kill you. The second one is that it's hugely expensive because it involves millions of devices that are somewhere. You don't know where. So if something goes wrong, you cannot easily update that now. I mean, we're just starting to have telemetry units and software over-the-air updates. Like Tesla is the pioneer of this whole new ecosystem. But what do automotive know? What automotive knows that how to make software and hardware in a way that it doesn't kill you. So they decided to take an approach similar in a way that they approach that car doesn't kill you, to take care of the cybersecurity. People who take care that the car doesn't kill you are called functional safety engineers. And they ensure that there is no sudden movement of the car and that your tempomat does not go to the 200 kilometers an hour without any actual input. Those people, their first step is this hazard analysis and risk assessment. Basically, they take a look at the whole vehicle and then any subsystem in the car to see how can it harm the passenger inside or any other person on the road. And then people in automotive industry said, okay, fine, we're going to do a similar approach for cybersecurity. That means that we have threat analysis and risk assessment while they have hazard analysis and risk assessment. They have some safety levels, some safety not all components are on the same safety level. Let's say your radio in the car is not necessarily on the same safety level as your emergency brake, right? Emergency brake has to have failovers, and you can believe what it has to have, like full state machine description. You have to know all the error state, all the fault states, and how to behave it. It has to be completely deterministic. On the other hand, obviously, your Apple CarPlay does not behave in that way. Same thing goes for us. There is a cybersecurity risk assessment, which takes into consideration the impact for the customer, in our case, because we produce the components that goes into the vehicles. Feasibility, like, okay, fine, we can hack it, but what it takes to be hacked. And the risk level, so basically, is it annoyance or it will kill somebody? And from there it goes further and further, but the bottom line, from there we define something called cybersecurity goals. Those are like some broad statements that says what you want to achieve with the cybersecurity in automotive. And then you go for the cybersecurity concept, architecture, and then design and cybersecurity controls. And what I want to show you in this talk is how we start with that, and how in the end we actually test for the cybersecurity, what we do. Us and now everybody else in the automotive industry. So, you take one component in mind. Let's take powertrain. We will examine powertrain because it's from cybersecurity perspective, it's relatively simple. You have usually one major input, which is CAN bus. It's a communication interface that goes over inside the car. That's a network which is defined 30 years ago, and all those nice things that we know in the cybersecurity world for the IT, we do not have in automotive. Meaning, we do not know who sent the message. We do not know for sure easily who sent it, or maybe was it replayed. It's a difficult question. The reason why now automotive goes somewhat to the automotive Ethernet, which has all the things that we know, but although the broad throughput of the CAN network is not that big, it's really fast in response, and you want that when you have a crash and you want airbags to be activated, right? So what are the basic functionalities from communication standpoint of powertrain? It controls the vehicle that it doesn't veer off, right? It communicates with inverter inside. If for the regenerative braking, it needs to communicate with the battery management system to see when and how to charge the battery. If there is some fault, it needs to bring up the light, like those light switches behind the dashboard, that something is wrong. So actually, although it's a relatively simple device from the cybersecurity perspective, and there is only one communication interface usually on it, there is so many communication network features on the device itself that you need to take a look. So this one is interesting for us, let's say. Well, basically, function. It transmits driver's accelerator input as a torque request. So on any, let's say ID3, you push the pedal. It's not physically connected to the inverter. It sends a message. It sends a network message. Please give me more power. And then the powertrain says, okay, somebody sent me a message that he wants more power, and it goes faster, right? You can see now with what I said before. By default, we do not know who sent this message. So in CAN network. So there is an extension above it. And then we start. Okay, this is the threat analysis for us. We have powertrain. There is some communication. There is only one communication network for which we are responsible here. What is the threat? Somebody can come in and record the communication and then replay the messages. Then we extend. What is needed to be done here? to somebody achieve this? Either compromise some other device in the network of the vehicle, because remember now all the vehicles are connected to the internet, or gain the physical access to the actual wires. And then from there, you grow your tree. And this is just for one feature. So, for example, we can gain physical access to CAN bus. Okay, how do we do that? There is actually one standard way, which is in every car. That is OBD port. You can connect to it and try to see error messages. Or you can maliciously do that and clamp the wires somewhere, right? But on the other hand, if somebody manages to compromise another entity in the network, he can maybe sniff traffic and see what's happening. This happened in the most famous case in 2015 for your standard Jeep family SUV. What happened when you not connect all the things? Bottom line, they had telemetry unit exposed to the internet, which they didn't patch, and some remote procedure call port was open, and if you were on the same telecom network, you can just nmap and find all those devices on the network. Use one Python script from exploit.db, get on the device, and from there you're on the inside of the network of the car. Normal network of the car should have some cybersecurity controls in place, because as we are doing this for the one component, because we are a component manufacturer, let's say Volkswagen or I don't know, Toyota needs to do this on vehicle level for each component. And they have to do whole network to see what of the interactions, what's happening. And this is possible in vehicles because it's relatively stationary network. If there is a change in the network, change of the communication of the network, you should know about that. It's not like in IT systems where you update Chrome and your EDR starts behaving weirdly because there are some weird calls around the network. So, what happened for the Jeep? They compromised infotainment from telemetry unit to infotainment, and then from infotainment they managed to update what's device that's called the cybersecurity gateway, which was not cybersecure, because there was no digital signing on the device, and they managed to patch the firmware and send the message to the internals of the vehicle, for example, to the powertrain. And when you all have this in mind, that we are developing one component here, but we need to be prepared that in case that there is a compromise of existing network. Or the wireless attack vector for the components which I place here, maybe not for the powertrain, but if you're developing infotainment, if you're developing telemetry unit, even some weird stuff, there was some wireless attack on those tire pressure sensors because that sends wirelessly data to the network. So you have to model everything. But for us, for this case, everything come down that, okay, fine. Somebody will manage to log the data that is sent in the network. And then what? Obviously, they need to analyze it. This data is not publicly available. Security to obscurity, which is not. So they need to figure out how the network works. So what usually you have as a manufacturer is something called CAN DBC. It's a CAN message database where you describe all the messages. So you reverse engineer your CAN DBC and try to figure out what message means what. How do you do that? In a brute force way. There was actually excellent presentation besides Osijek 2 years ago, where one of the guys from the car hacking village said, how do they do that? Well, they basically plug into the CAN network. He rents a car, plugins to the network, and start fuzzing and hopes that something will happen. And what happened to him? is that he managed to get odometers from a rental car from, I don't know, 2,000 kilometers to 99 kilometers. And then he had problems with returning the car to the rental company because he made too many kilometers. So yeah, that's what we are fighting against, amongst other things, right? So how do we protect for that? Obviously now, we said, okay, we really don't want to have a situation where somebody is able to replay a message or for more torque, for basically go 200 kilometers per hour now. So we need to ensure that we know who we are talking to, that at least we can only receive messages from the one component that we know that we are allowed to receive those messages and nobody else. How do we ensure that? There is actually, let's say, new layer on top of the communication on the CAN network called SecOC, Secure Onboard Communication. Fine, checkbox. Okay, checkbox. Now we moved forward. We will reduce the threat level like that. What we introduced: message authentication codes, timestamp encounters, challenge response mechanisms, session keys, maybe rolling codes, or maybe in more advanced way, HMAX, not just MAX. But now what we have introduced into the system? Cryptography, and random number generators, because we have to have true random number generators. But like, where do I store session keys now? Well, that means that I have to have a new device inside my device. Now I have to have HSM. Now I have HSM, and then I don't want you guys to take my device and all of you hackers here and me in my previous job and steal my secrets, because if you steal my secrets, it's not just an update. I have to recall, my clients need to recall all the devices back to the workshop to be reconfigured. Okay, we have a new problem in place. That's disclosure of cryptographic keys. Where do we store them? Well, obviously now there is a physical access to the device. When you actually physically access the device, how do you flash? How do you change memory? How do you read memory? You need to read memory if you want to update the firmware of the device. That's something called UDS. And that's a legitimate function of any ECU. There is a JTAG, there is a debugging port, because you need it, at least in development. There is a direct memory access with those like pins and everything, and maybe even desoldering the chip itself and doing the memory analysis. Okay, now we have new layer, one more layer of the complexity, and we're just talking about one feature of one device. Okay, to use this, there is a hardware fault injection. There was some really good papers and really good talks how they managed to avoid with currency injections on the micro to step over the authorization of the UDS. What do you do? Then you introduce a new separate chip which is made not to be vulnerable to that, which is basically HSM. And then, okay, we need to store data in HSM. That adds a new complexity. Again, we need to store, we have to inject the keys into the device somewhere. It's either on the end of the line of the production or in the chip manufacturing itself. If you're a really, really big vendor, then you usually talk with the chip manufacturer itself, which will then put keys inside by making a chip. But that means that you have whole backend infrastructure, which we have, which is normal IT backend infrastructure, which deals with the key injection facility, key storing, and all those things that you all guys know from the bank business, and especially car production business, how do you handle the keys, right? So, yeah. And our, let's say, greatest fear is extraction of the private keys. And then we need to calculate is the investment into the HSM and the chip. How does this brings up the bill of material cost, and how much would it basically cost us to recall the device, the shame that we got hacked and everything else, because it's not easy, not so easy. What you see here, that is the code is really interconnected with the hardware, so we cannot iterate really fast. It's really hard. Once we decide for the hardware, we have to build from that. There is no easy fix, okay, we'll just change configuration. No, like you chose microcontroller, you chose HSM, you drew a board. There is like 10 people which did the simulations of electromagnetic radiation on the board to make sure that everything is okay, the heating resolution. So, for example, just the task of removing JTAG conduits of the board is not that actually simple, because you will change the electromagnetic properties of the board. One really cool tool that we are actually is one of our sources for this whole structure is the Embed framework. It came out, I think, last year. So you can, for any embedded device, you can like choose what you have. Like, does the device include microprocessor? Yes. Do you have external memory storage? Yes. Do you have a bootloader? Yes, and so on. And then it goes like attack matrix, similar. I mean, and it says which are applicable threats for you. So you have to model all those threats, take care of them, and from there derive cybersecurity requirements and mitigations. For example, for the bootloader, secure. If you have a bootloader, that means that you have to have secure bootloader. Secure bootloader requires hardware root of trust. How do you achieve hardware root of trust? And now we are here. This upper part is just one small snippet of our attack tree for just one device, which is not that complex from cybersecurity perspective. And there is more, actually. But now we're here. We saw what are the threats, and now we can define the goals. Let's say, one goal that we can have is if one vehicle gets hacked, that not all vehicles got hacked immediately. So that means, for example, specific keys per device. From there, we then define cybersecurity technical concept. That basically means higher level requirements. From there, we define software and hardware cybersecurity requirements. From our perspective, we have, let's say, our own. We are one stakeholder in the whole ecosystem. Our client is another one. What that means? Recall, let's say, compromise of those crypto keys is really high problem for us. But if the client is not owner of those keys, maybe that's not so high problem from him. But he has other perspective. But let's say that when you go for the technical requirements, and once you agree with the customer, we are talking about between 500 and 1,000 plus full technical cybersecurity requirements which software developers need to implement. And you have to track it somehow that we achieve those level of cybersecurity assurance, whatever that means. But with that paper, our clients will go to the homologation body with all those papers is in a similar manner done as we are doing. For each of those components in the vehicle, they will go with a stack of papers, hopefully not actually papers, to the homologation body. They will put it there. Okay, this is our documentation, and this is the crash test, and this is ecological test. Can we now please put the car to the market? So this is the structure that we got from all the previous slides. There is some generic goal. We want to prevent unauthorized access to the vehicle powertrain. We claim that we managed to ensure that only authorized entities, meaning us, can communicate with that ECU. Then requirement says implement message authentication, that's echo C. Use secure boot that firmware doesn't get compromised and changed as in Jeep hack. That there is some certain roles, because maybe at some point in time, in 10 years, have in mind that vehicles are on the road for 10 plus years, and we need to take that into consideration, that in 10 years maybe we'll have to roll the keys. But not everybody needs to have access to roll the keys. And from there, we defined like fully specific things, like that message needs to be signed by the HMAX 256, and so on. Totally funny thing. Year ago, ChatGPT didn't know anything about automotive security. Now it knows. So you can like do like generic examples with that. And now, once we have requirements, then we go deep down into the like how do we actually implement boot manager, how do we communicate for the keys, how do we exchange the keys, and so on. This is documentation from one really big vendor, publicly available, where they describe how their libraries do and how the whole system communicates. And there is a lot of that. So remember, up to 1,000 cybersecurity requirements that need to be covered technically for one project, which is not so cybersecurity hard to do, in a sense. I cannot, like, if you go for infotainment, which has wireless, Bluetooth, USB port, complexity goes out of the blue. So once we hopefully now developed, we go for the other side of the V model, that's verification and validation. Interesting thing is that that ISO standard that I said in the start actually states this, that this is what you need to do. Functional testing, you ensure that authorization on the device actually works. Vulnerability scanning, which is topic by itself. Fuzz testing, literally says you have to fuzz test, and you have to do penetration test. Vulnerability scanning for the embedded device is really hard, and it's not so easy because most of the code is either proprietary, and scanning of the interfaces is not so easy without like deep knowledge of how things work. There is no standardization for the most part. Maybe in some other parts of the embedded world it is, but in automotive not so much, because vendors will specify how communication needs to work, because they will buy something, let's say from us, from Bosch, from Continental, from, I don't know, Infineon, and all those things need to work together, so they make a specification which is specific to them. What we see in the market now is that a lot of companies are rising and doing some vulnerability scanning and now fuzz testing and penetration testing services for the vehicles and components of the vehicles. We are trying to build our own fuzzer, because all the tools in the what we saw are not good enough, let's say. Laura sitting here helped me before with that, so thank you. We're still using it and developing. But basically what we do, we try to, so we know what we put inside, that's the difference. It's not completely black box fuzzing. We know that's DBC file. We know what are all the messages that can occur. So we use that, we test it, we parse it, we get all the CAN ID, we mutate payloads, we try to do like it's still most, from the perspective of like modern fuzzing is still more or less simple. Bit flip, byte swapping, insertion, deletion of bytes, random inserting randomness, while maintaining or not maintaining the structure needed for the message itself, depends on what we want to achieve. And then from that it goes to the socket CAN library. From that it goes to that small device, which is called PIC CAN, and then it goes to the device. One big problem with this whole setup, unlike the IT system, you cannot easily, or most often you cannot emulate the device, because it has sensors. It expects some communication in the background. There is huge hill rigs, so that's hardware in the loop, which simulates the networks of the vehicle, where you need to simulate that. And then for you'll use usually proprietary debuggers that are made by the chip manufacturers, where you connect to the JTAG, and we try to monitor for the changes in the like registers and flow of the code. Those things are hugely big and expensive. We would like to find a way which is more open source. And yeah, we're fuzzing. Like we leave it for like I don't know, a week or something. We managed to crash a lot of things. Similar as in IT, there are layers. There are layers of code which were written by our developers. There are layers of code which are like kind of like OS. You don't do, in a way that you don't want to write Ethernet protocol each time you do network communication. Similarly, you don't want to write each time the basis for the CAN network communication. So you probably use some libraries. And then between like things can happen between these, especially between those two layers. The issue is speed. We are working on improving the speed as much as we can. But yeah, it's work in progress. Hopefully, actually, we'll open source it at some point when it gets a bit more stable. And then we move to the pen testing. Pen testing is kind of similar to your normal pen testing, but with additional hardware layer, let's say. The business logic can still occur. For example, there is a CAN message that says, read me part of the memory, because in that part of memory usually is that some log message. And then you do buffer overflow there, or you read a bigger part of the memory than expected, and you manage to read, let's say, cryptographic keys if they're not stored properly in some secure place. That actually happened. Think about that again, Jeep. So that logic still applies, but you have additional layer of JTAG test points, because when the device is done, when it comes out to the production line, there's supposed to be some test points where you can check the quality that everything works. And for example, maybe from those test points, you can actually access part of the memory to see that, because you need to test that everything is there, but from penetration testing perspective, that's like really nice entry point. And yeah, things happened. It's not that we are doing that in our separate bubble. Lexus, Toyota, whole those their telemetry unit provider got hacked, and you can do bad things with the cars. Ford says cars with Wi-Fi vulnerability are still safe to drive. On the other hand, this one on the right side, because of that regulation, Porsche decided to stop the sales of Macan SUV earlier, and they had a gap between the earlier version and new generation, because they couldn't prove to the homologation body that it was good enough with cybersecurity. So, and the thing that all of you can think, and I mentioned that in Varaždin, we need to patch those things. There is an end of support for Windows 10. There is now end of support for your car. And the big question is what will happen. Like, no OEM is sure when end of support happens, then what? This kind of doesn't apply to us, because we need to support our OEMs, but it's more questions for the OEM. Until when they will provide security updates for your vehicle, and what will happen? Now, usually what they think, at some point, let's say in 15 years' time, they will say no security updates, they will cut you off from the internet, and your internet connectivity won't work. And that's why you can also see those all bizarre subscription thingies in the vehicle, because how do they handle software development from IT perspective of, let's say, our mobile phone that we all now expect that we have in a car, because each time you have an update, those guys that test the component that it doesn't kill you need to do all the things again and again. Yeah. So it's a development with real life impact, both from cybersecurity and functional safety, because it can slam into the wall, right? If we do our job badly. Yeah, that's it. Any questions? And do you have your mic?
Thank you, Jagor. The gold one.
Thanks. A great presentation, by the way. So you mentioned that some things can come over the wire, some things can, be a physical misuse, and maybe, desoldering something and, tapping some JTAG or something to actually do some harm on the car. So, and you were mentioning like systems for holding cryptographic keys and etc. So, do now these requirements require that these critical systems or chips or whatever have some kind of tamper-proof detection, and that if you try to mess with them, they get fried or stop working, or any kind of tamper-proofing for those devices, so that for the attacks that do not come over the wire but come physically, the car itself would not allow this, or would get not useful after that.
Yeah, okay, that's the idea. Yeah. So, but think of it like this. In that case, that means that somebody will actually come inside and put the top plate, take out the device, remove the top plate, desolder something and you need to have time to actually put it back together once you did something bad and put it back. So, I mean, from my perspective, yes. To answer your question, yes. That's why we have HSMs. And the second topic, bigger maybe topic for me, is that even if this occurs, even if they manage to get something, because at that point they disassemble the vehicle. But the knowledge they received from that one should not be able enable them to hurt another vehicle which is still on the road.
Yeah. Well, we saw that this kind of things, broke DVD players, Blu-ray player encryption, because it's a trusted client issue. Once you get, the manufacturer keys, all bets are off, basically.
Yeah, I mean, so the idea is, okay, fine, you managed to break everything, you solder back a new chip, I don't know, find some vulnerability, and you manage to update your particular ECU with something new that is not ours, let's say. Even if you manage to do that, you should not be able to do that on the other vehicle without repeating actually the whole procedure again. Yeah.
Yeah. Last thing, so since you said that it's extremely, for the safety perspective of it, it's very important that the functions basically work. And so, is there any kind of idea that the basic functionalities that once were formally tested, they are baked into some kind of, I would say like a backup, FPGA or something, and that, if the system detects any kind of anomalies, like potential, hack or something, those things are basically just wiped, and you just default back to the original factory setting, for old car safety features.
There are two concepts you can apply here. So one thing is that actually is ongoing, regardless of the cybersecurity and for the functional safety part, is that there is ongoing, for example, some check of the integrity of the whole memory. And if they see that memory has changed, then they will raise a flag and your dashboard will light up actually. And in the modern times, that data will actually go to the vehicle security operations center, because that's now a thing. And then you have on some devices, if the manufacturer, if the client specifies, you can have AB part of the memory, when then you swap. If the B memory is still intact, then you swap back to the A. So yeah.
Thank you.
Thank you. Oh, I didn't say sorry.
Hi, just a quick question. When you are sitting down to consider these types of threats, do you have some sort of formal system which helps you to?
Sorry, do I have some?
Do you have some sort of formal approach or system which helps you figure out, or you just brainstorm and everybody throws idea? Yeah, this could be.
Yes
affected.
and no. We use our previous experience. As I said, my previous experience was pen testing. At the moment, currently, there is no, let's say, there is a, let's say, minimum set of things that you need to check, which is provided by the standards. That's not nearly enough, and that's not updated enough. So we try to track a lot of things on with researchers. But for example, unlike subscription services now that you can subscribe in IT for threat intelligence, there is no, as far as I know, there is no, let's say, threat intelligence with automotive. There are some attempts. There is now automotive vulnerability database, similar as a standard vulnerability databases, which is set up by Trend Micro. There's like, we are going in that direction, and there are tools to for threat modeling, which are used some formal, like it forces you to do formal methods. But when we asked all those, like, okay, you provide a tool, but from where do we get the data? And they're like, on your own. So yeah, I would say we're a couple of steps back from that embed the attack tree from the embed framework. That's completely new. That's a big step forward in some formalization.
Thank you.
Really interesting. I'd like to ask you if one day I can be invited to try.
You can,
yeah. Anyway, I have a question. The aviation industry is facing the same, let's say, topic.
Yeah, I guess
they
so,
are
yeah.
approaching the same threats. And essentially what I've seen is the automotive industry and the aviation industry base everything on a sort of flat network where you attach some modules somehow. More or less.
Yeah.
Yeah. So the question is, what about the compromise of the supply chain, and what if you have an insider who will share all your sensitive information?
Yeah. I would okay. There's two questions here. One, do we? Yes, all modern cars have separated networks. So 5, 6, 7, I don't know. There is like your safety relevance part of the network, and no messages should be allowed, let's say, from the infotainment or telemetry unit to that. They're actually, usually they're in the middle, let's say there is a firewall kind of device which filters what goes where. So yeah, in this probably I guess the same goes for the aviation, that they have some, let's say, safety part of the network, and there is the other part of the network, in pretty much in a similar manner as you would do a DMZ and like your core network. The second part of the question, sorry, I forgot.
If you have an insider.
Okay. Then I'm trying to behave, and we are trying to behave as we were behaving in my long time previous life in car business. So you will have your crypto keys and HSM on the back end, so nobody can actually access it, like dual controls and stuff like that. Yeah. On the other part, if some developers get mad and put code inside, yes, we have code review and everything else like that. There is huge now business in similar manner, and there is an IT for software decomposition, which kind of works. It works good for the infotainment stuff, for telemetry units, because mostly they're on Linuxoids. For fully embedded, it's really hard to do, because it's like one blob of binary code, and it's specific. The structure is specific to the microcontroller that you're using. But if you are wondering where the BlackBerry as a company is, it's live and kicking in automotive actually. They have a solution for like a hypervisor for your core device where you have isolation with the containers and they actually have a product which does the software decomposition that you can use if you need it. Again, I'm looking at that from different perspective because we are the one who build the code. But if I was automotive manufacturer and you receive the binary from somewhere, then you should check as much as you can.
Thank you.
Thank you for the presentation. It's great. One question. If I'm a hacker, I want to earn money.
Mm-hmm.
So what's your opinion? What could be the worst scenario? If I obtain, let's say, if I obtain enough information, is it possible to block like all the cars and ask for ransom from manufacturer or?
Yeah, I would say, so I had this discussion a couple of times and I was in Göteborg for some connected vehicle conference there and we talked about that on the lunch. And we all agreed that the money is not in attacking actual user of the vehicle because for me, my vehicle stops working, I'm highly annoyed, I'm angry at the company, but bottom line, I will go to the service shop and say, fix it. And they will probably need to refresh everything. And from my as end user perspective, most likely the event will be as some big problem with the engine, I don't know, or gearbox, whatever, or something. Or my axle broke down because I speeded over the bump. But if that scales, that's a huge cost for the OEMs, for the manufacturers. And then I think if you manage to get into the position that you block, if you brick the vehicles, you can extort the manufacturers for the money and say, sorry, like, give me $1 million or you will have a cost of 100 million to recall all the devices. Yeah, so I think that's the crime perspective that's possible. But on the other hand, it doesn't need to be crime perspective. We had a colleague with a brand new car from Volkswagen Group. He clicked, there was a pop-up, it was update. He clicked update and the car bricked.
Yeah, thanks.
Any hands? No?
There.
Yeah. At the back, yeah.
Yeah, hi, thanks for the presentation. It's really interesting to see. Just wanted to ask you, like, do you have any easy ways of disabling internet access and general connectivity of the cars when, like, in 15 years, as you said, no one's going to be patching them probably? And I would really like to have my airbags deployed instead of it mining crypto or stuff like that.
Yeah,
so.
I'm kind of wrong person to ask because that's not what we're dealing with. But there is a concept of fuse registers. So you write only once and you cannot. So once you write something in, you cannot change it. The Tesla, I saw some presentation online basically. For example, Tesla uses this technology to fuse the production vehicles. So they for their employees, I think, have let's say test vehicles where you can more easily update things and maybe even more importantly roll back updates, which is not possible in a production vehicle. And then you fuse the register, and then you cannot do it anymore. So I kind of expect it's a software command for a physical thing. So I think probably the same thing will happen there.
Do you maybe think is that like a practice that's currently used by automakers to plan for, like, when they don't plan to patch things anymore?
I'm not sure that they. I mean, they're supposed to have some plan. They're not sharing that with us because that's their internal secret knowledge. But what I know when I talked to some OEM manufacturers is that it's a huge issue for them and they're not 100% sure how to do it. Sorry, OEM manufacturers, original equipment manufacturers. So we are tier 1 supplier to the car production companies, what you think of car production companies, like those big groups. In our world of IT, that would be more like integrators. They kind of buy everything from everybody else and they integrate it.
Cool, thank you.
This will be the last question because we have 6 minutes to the next presentation. So see you later and thank you, Jagor.
Thank you.